Hello, very good evening to all of you. So today I am going to give a second lecture on the torsion of shaft. In my early classes, I have explained the basic torsion equations, how to find the angle of twist, and resisting torsion, resisting torque, and how to find the strain energy due to torsion. That was covered in my early classes. In today's classes, I will explain about the in case of bearing bar, how to find the angle of twist. Suppose I have a bar, its dia from one side it is different to the another side. Then indeterminate structures like bars in parallel, bar in series, how the torsion varies, how to find the angle of twist, and how to draw the torsion diagram, torque diagram, twist diagram, and how to find the torque in case of composite shaft. That will be covered in today's lecture. So let's start from one. So I have a one bar. This is my tapering shaft. Its dia on one side it is d1 and on other side it is d2. It means its radius is r1 and radius is r2, and there is a equal and opposite torque. So my torque is same on both the side. It is equal and opposite for the equilibrium. So now I have to find the angle of twist in this case. So to find the angle of twist, since its dia is varying, suppose I have considered a small stretch strip of thickness dx at a distance x from this spot. So this is my elementary strip of having a thickness dx, which is x distance from this end of the shaft. So if I want to find the angle of twist for this elementary strip, then my formula is d upon j is equal to n theta upon l is equal to f upon r. That I have explained in my earlier lectures. So this theta will be equal to TL upon nj. So this is the formula of theta, angle of twist. So here, if I want to know the angle of twist here, then since this t is constant here, it will be like this. So my t is constant, and suppose there is a delta theta is the angle of twist for this elementary strip. So it will be equal to t into L, here is dx, divided by n. N is the modulus of rigidity of a material, that is constant, and j is the polar moment of inertia. So polar moment of inertia is equal to, suppose here it is zx. So my formula is pi d4 upon 32. This is the formula for polar moment of inertia. Suppose if I write it in terms of radius, it will be pi r4 divided by, it will be 2. So it pi into 2r raised to the power 4 upon 32. So it will become pi r raised to the power 4 upon 2. So this is my polar moment of inertia formula. So here this r is rx. So rx is equal to r1 plus difference of this r2 minus r1 divided by this length, r2 minus r1 divided by this length L into this x. So these are two similar triangles. One is this bigger triangle, another is this one. So from the property of the similar triangle, I can find my radius here. So it will be equal to r1 plus r2 minus r1 upon L into x. So I can put the value of rx here. So it will be r1 plus r2 minus r1 divided by L into x. So This will be my value of my Rx, and the formula is r raised to the power 4 into pi divided by 2. So it will become, so this will give delta theta. So this is my formula. Suppose if I want to know the total angle of twist for the whole shaft, then this is for this elementary step. If I want to know the total angle of twist from this end to this end, then I will integrate it from x is equal to 0 to x is equal to L. So then integration of this from 0 to L, this 2t, this 2 will come here, 2t upon n and pi. This will be outside, and inside it will be dx upon r1 plus r2 minus r1 upon L into x raised to the power 4. So the integration will be, this will be 1 upon x raised to the power 4. So it will be x raised to the power minus 4 plus 1 divided by minus 4 plus 1. It means x raised to the power minus 3 upon minus 3. So like this, the integration will be this. So if I put the value of L here, so it will become, finally my equation will become like this. Suppose if I convert this radius in terms of diameter, then I will arrive here in this equation. So this is my final product. So the final formula is this: total angle of twist theta is equal to 32 TL upon 3 n pi d2 minus d1 into 1 upon d1 cube minus 1 upon d2 cube. So this is my total angle of twist. So it means if I have a tapering shaft of varying radius dia from one end to another, and I have to find the total angle of twist, that will be equal to, in this case, my formula for total angle of twist will be theta is equal to 32 T is the torque length upon 3 n pi into d2 minus d1 multiplied by 1 upon d1 cube minus 1 upon d2 cube. So with this formula I can find the total angle of twist of this tapering shaft having dia which is varying from d1 to d2. So in case of normal shaft, as we have discussed in the earlier lecture, that was equal to n theta upon L is equal to T upon J. So theta was equal to TL upon NJ. So in case of shaft of constant dia, then it will be 3 TL upon N, and polar moment of inertia will be pi d raised to the power 4 upon 32. So that was the formula in case of shaft of constant dia, and in case of varying dia, this is my formula. If I put d2 is equal to d1 in this formula, then it will be, if I put d2 is equal to d1, then is equal to d, then my formula will be the same as in case of a constant dia. So let's come here. This is a non-uniform or varying torsion. Suppose I have this section, I have two shafts, one is AB, another is CD. Both are rigidly connected as they are behaving as a single unit. So here my cross section is also varying and my torsion is also varying. It is T4, T3 and T2, T1. So it is varying T1, T2, T3 and T4. At this end it is T4, it is at C, it is T3 and here it is T2. So in case of non-uniform torsion, like this, the bar need not be prismatic. So applied torque may vary along the length of the bar or shaft. So in case of non-uniform torsion, my torque can vary and my bar is not need to be prismatic. So how we will do the analysis of this? The torque Ti for any region in a cross section of the road is equal to the algebraic sum of the moment of all the external couples acting about the line, geometry axis of the road and up to one side of the cross sections. What he is saying, as we have discussed in stress and strain chapter, composition for finding the displacement like this, as I have explained here. Suppose it is P1, this was P2, P3 and so on, P4. So for finding the total displacement, my formula was P1 L1 upon A1 E1 P2 L2 plus upon A2 E2 plus P3 L3 upon A3 E3. So that was my formula. And in that case, so what was my procedure for finding the force at any cross section? So in that case, I will take the algebraic sum of all the forces starting from one end. Suppose if I start from this end, then I want to know the force at this, then I will consider all the forces which are acting on this side of the sections. I can start from either way. I can start from right to left or left to right. If I want to know the forces at these junctions, then I will consider all the forces which are acting up to this junction right from the left. So that was the procedure. Likewise in torsion as well, my practice is that if I want to know the torsion here at this junctions, so that will be equal to the algebraic sum of all the torque which are acting on one side of these junctions. So suppose this is my x-axis, I want to know my torque here. So that will be the algebraic sum of T1 and T2. Suppose this is anti-clockwise. So as I explained in my early class, there is a procedure either way we can write it clockwise or anti-clockwise. Another method was that is a vector. Right hand thumb rule is that, so if it is, suppose if it is anti-clockwise, so anti-clockwise means suppose this is my shaft, this is my right hand, so I can put here, so anti-clockwise, this is anti-clockwise, and the direction of the thumb will indicate the direction of the torque. So this way also we can plot it. So it will be like this double headed arrow, and this is also anti-clockwise, so it will be like this, and here it is clockwise. So clockwise means this is my bar and this is right hand. Always use the right hand and see the direction of the thumb. So your finger will create the direction, whether it is clockwise or anti-clockwise. Your thumb will indicate the direction of the torque. So this way also you can plot it. So here it is, since it is clockwise, so clockwise is this is clockwise, and this thumb will, so it will be like this, and similarly it is also anti-clockwise, so like this. So this way you can represent your torque. If I want to know the torque at these junctions, so this will be equal to, since both have the same directions, so at this junction it will be T1 plus T2. If I want to know the torque at these junctions, just to the right of this, it will be equal to, since T1 and T2 both have the same directions, they are same direction, T1 and T2. This is T1, this is T2. So both will be added together. So T1 plus T2, and this torque is acting in the opposite directions. So this is my T3. So here the net effect will be, net force, net torque will be this minus this. Suppose this is 30, this is 20, so it will be 30 minus 20. If I assume that the sum of this is more than this, then it will be T1 plus T2 minus T3. So net torque here will be T1 plus T2 minus T3, and it will be, the algebraic sum will be, so this is more, it means it will act this way. So if I want to draw the free body diagram of this, it will be like this. For this AB portion, this is for AB portion. So I can represent it like this way. So this will just be the opposite of this. You just see the opposite of this. This is for AB. For BC, since it is T1 plus T2 minus T3, and this sum is more, so it will also act here. This will be T1 plus T2 minus T3, and the same will be equal and opposite for the equilibrium. So it is not required to see here. Exactly it will be opposite, T1 plus T2 minus T3. Its nature will be just opposite of this one. So you just see only this side here. At this, for CD, it will be, for CD, since this is more, so it will be like this, T1 plus T2 minus, oh no, this is for CD. This is for CD. For BC, it will be T1 plus T2. And this will be equal to, obviously, the torque here. So if I found my value of any torque in negative side, it means, suppose if I find T3 is equal to minus 20 kilonewton meter. What does it mean? It simply means that the direction which I have assumed there, that is exactly not right. So it is exactly opposite of this. If I assume the direction of T3 like this, and if I found the value of this, it means the T3 is not in this direction, it is actually in these directions. So this way we can calculate it. So this will be further illustrated in the numericals. So in case of non-uniform torsion, the bar need not to be prismatic and the applied torque may vary along the length of the shaft. The torque Ti for any region in a cross section of the rod is equal to the algebraic sum of the moment of all the external couples acting about the line geometric axis of the rod and to one side of the cross section of the cross section being considered. That's what I have explained. If I want to know the torque here, that will be the algebraic sum of all the torque acting from the on this side. If I start from left, otherwise I can say from the right side, whichever way. So the total angle of twist of one end of the bar with respect to the other is obtained by the summation So if I know the total angle of twist here, in this case the total angle of twist here theta d, so that theta d total angle of twist at this point d will be equal to the algebraic sum of the angle of twist of all the portions. So it will be theta for AB portion plus theta for BC portion plus theta for CD portion. So my total angle of twist will be the sum of all the different regions. So for same direction it will be opposite positive, and if it acts in the other direction, my torque is in different direction, so that will be negative. So whatever will be the total sum of the all the angles twist, that will the final total twist at this point. And this will be equal to, as we know, theta is equal to n theta upon L is equal to T upon J is equal to F upon R. That was my formula. So theta will be equal to TL upon NJ. So this is my formula. So for any sections here, if I want to know the theta of this one, for this regions, suppose this is theta I, this will be equal to torque here Ti, Li, N and Gi, if N is constant, and I will do the summation. So summation of all this will give the total angle of twist. So this is my formula. So total angle of twist at one end of the bar with respect to the other is obtained by the summation of in the general formula. So my total angle of twist, suppose at this point it will be the sum of this plus this. At this point it will be summation of theta of AB plus theta of BC. If I want to know the theta of D here, it will be summation of all this. So, and again so for this reason, separate reason, when we can consider my torsion is constants. So I can apply my earlier derived torsion equations. Suppose for separate equations, for separate reason, I consider my torsion is constant. So here for this portion my torsion is constant, for this portion my torsion is constant, for this region it is constant. So within any regions we can easily apply the torsion equation that I have explained earlier. T upon J is equal to n theta upon L is equal to F upon R. So for any separate regions, this was the formula for pure torsions. So my torsion was constant like this. So these separate regions can be considered as a case of pure torsion. So my torsion, this equation can be applied for any region specifically one by one. Suppose I have a different my non-uniform torsions. So this is just like a UDL beam, UDL in simply supported or fixed beam. So here my torsion is varying. This is T1 per meter length. My torsion here is T1 per meter length. So here it is a concentrated torque, and again it is linearly varying. So my torque here is varying linearly. It is T2 per meter length. So it is a linear, this end is fixed, this is free. So this is a case of non-uniform torsions. Then if I want to know the torque in any arbitrary cross sections of the rod, this will be equal to, suppose I want to know the torque here, this is Ti. So that will be torque here at these junctions Ti will be the algebraic sum of all the torques acting on this side or from this side. So if I start from this side, it will be equal to, these are my concentrated torques. Suppose I have number of torques like this, so that will be the summation of these torques. And then suppose here it is T into dx. For this ring it will be T into dx. Then I will integrate it from here to here, so that will the integration, And if I add all these, suppose I have number of like this torsion, it is bearing here also, then it will be summation of all that, and it is also includes here. So this is the formula in case of non-uniform torsion. Suppose I have a different case. In this case, my rate of intensity of torsion is varying. So torque is not constant, it is varying, and its dia is also varying. The cross section of the shaft is also varying. So here the torque is varying as well as its cross section is varying. So its dia is varying. So in this case, my angle of twist will be derived like this. Suppose I have considered a small elementary sections. So this is my small strip, this bar I have taken. So this is length is dx. So suppose if I have a torque here, it is tx. So torque here is tx. So tx is basically the algebraic sum of all the torques up to this point, right from here to here. So it is, suppose it is tx. So my torque is tx here into length is dx upon n. N is the modulus of rigidity into j. J is the polar moment of inertia. Suppose it is here jx. So that will give the differential equation angle d theta for this strip. And if I integrate it from 0 to L, suppose this is length, total length is L, then it will give total angle of twist. This I have considered. So this Tx is basically the algebraic sum of all the torques right up to these sections. It will be T. This is, suppose this, the direction opposites is T minus this is T into dx right from 0 to x. Nature is, so that will be Tx here. So I will put this value Tx here into L upon n into j. This is from T upon j is equal to n theta upon L is equal to F upon R. This was the formula. So from this will be TL upon Nj. So here I can put the value here. So this torque is at a distance x from one end, and Jx is the polar moment of inertia of that distance. So total my angle of twist will be, if I integrate it, I will get this. Next is statically indeterminate torsional moment. So statically indeterminate torsional moment. So how we can do the analysis of this, that I will explain here. Suppose I have a bar. These are two shafts. One is dia is D1, this is D2, and both are properly coupled here. So they are rigidly fixed at A and B, and a torque is acting at this C junction. So here torque is T is acting. Its length is A, its length is B, total length is L, and this torque T is acting at these junctions, and I have to solve this problem. So how I can proceed? First of all, suppose I have released this and I apply this torque T2 in place of this. So it will be like this. So in this case, to solve this problem, I need one more equations. One is my static equilibrium, and in addition to this static equilibrium, another equation is also required. That is the equation of compatibility. Compatibility means my this theta c for both will be the same. So theta will be same. It means since both the ends are fixed, so my theta a, angle of twist at a and angle of twist at b, that is equal to 0. So this is my equation. It means my theta c at this, it is same for both this part and for this part. If I want to know the theta angle of twist for this AC portion, it means be, so suppose the torque here is, so let's, before doing this, draw the free body diagram and properly represent the torques. So for this CD portion, this is clockwise. So clockwise means this is my clockwise. So if you see, this is my right hand and this is the clockwise direction of the finger. So my this thumb, this will indicate the direction of the torque. So this way I can plot it. And here it is anti-clockwise. Anti-clockwise means this is my right hand. Put you this shaft here. This is my right hand and this is anti-clockwise directions. So it means this direction will be like this. And at this end A, the direction of the torque is clockwise. Clockwise means this is clockwise. This is clockwise. So clockwise will be represented by this one. Here I can easily draw the diagram. So for AC portion it will be like this. And for CD for CB portion it will be like this. So if it is here like this, it will be opposite of this one. So if I find my theta angle of twist for this AB portion, this is AC and this is CB portion. So theta for AC portion will be theta for AC portion plus theta for CB portion. So that will give the total angle of twist here at this, because this one end is fixed, another is free. So and a torque is acting here. So my total angle of twist here, that will be the algebraic sum of the angle of twist of this AC portion plus CB portion. So this will be theta B and that will be equal to 0. That will be equal to 0. So theta AC plus theta CB is equal to 0. So theta of AC portion will be equal to n theta upon L is equal to T upon J. So theta is equal to TL upon NJ. So theta for AC portion will be, theta for AC portion will be, so torque here is, it is T1. This is T1 and this is T2. It will be T1 length is A upon N and suppose its J is J1. So that will give theta AC and theta BC will be equal to, it will be equal to T2 into length is B upon N into, suppose its polar moment of inertia is J2. So if I put the value here, so it will be equal to 0. And since its direction is opposite, so it is just like a tensile force, it is just like compressive. So its nature is different. So if I say it is positive, it will be negative. So it will be negative. So if I put both the value here in this formula, it will be T1 upon A upon Nj minus T2 B upon Nj2. will be equal to 0. So this will be equal to 0. It means this equal to this, or I can say theta of AC, and they are equal and opposite. So they are equal. So from here I can derive one equations. T1 is equal to T2 B this and will cancel each other. So this will be T1 is equal to, suppose I have the same modulus of rigidity. So T1 will be equal to T2B into J1 upon J2 and upon A. So this is equal to this one, and another equation is this. So this is my one equations. This is equation of compatibility. My angle of twist here is equal to this one, or otherwise as can say my total theta B here is 0, since actually both the ends are fixed. So with this condition of compatibility I have derived one equations. Another equation is the condition of static equilibrium. What does it says? It says that this T1 plus T2 both have the same directions. T1 plus T2, that should be equal to this T. So this is my another equations. So if I put the value here, if I solve both the equations, then I can find my T1 and T2 in terms of T. So this is equation number 1, this is equation number 2. I can solve these equations. So from this equation, this is the condition of static equilibrium. So for static equilibrium, T1 plus T2 is equal to T2, and this is theta B is equal to theta AC plus this is equal to 0. So from this I can find these equations. So after solving both equations, I will get this one. So this is T1 plus T2. Suppose if I have put the value of T1 here, it will be T2 B upon A into J1 upon J2 plus T2 is equal to T. So T2 will be common. So it will be B J1 upon A J2 plus 1 is equal to T. So it will be T2 into A J2 B G1 plus A J2 is equal to T, and T2 will be equal to T into A J2 upon A J2 plus B J1. So this is the value of T1. Similarly, the value of T1 will be equal to, as T1 is equal to this, if I put the value of T2 here, so I will so T1 will be equal to T2. T2 is T A J2 upon A J2 plus B G1 into B into A upon J1 upon J2. So here this A and A will cancel each other, and J1 and J2 also cancel each other. So it will be T into Bj1 upon Aj2 plus Bg1. So this will be T1 and this is T2. So after solving these equations, I will come here. So if the dia is same, if D1 is equal to D2, D1 is equal to D2 and D, then suppose if both have the same dia, it means, so it will this will be, if both have the same dia, then it will be T into A J2 plus A plus B into J2 or J1. So it is equal basically, so J and J will cancel each other. So it will be TA upon, and this A plus B is equal to total length. So A plus B is equal to, this A plus B is equal to total L. And similarly this is T2 and T1 will be equal to similarly TB upon L. So they are just like analogous to fixed beam subjected to point load. Like I have a fixed beam and this load is acting here, W, it is A, it is B. This will be equal to WB upon L, and here it is WA upon L. So maximum shear stress for each part are given below, Fs1 upon Fs2. So that will be corresponding. Suppose if I have a torque as the formula is T upon J is equal to F upon R is equal to n theta upon L. If I want to know the maximum stress for each portion, so that will be F will be equal to T upon J into R. So if I want to know the F of this AB portion, it will be F of shear stress of AB portion will be equal to torque. This is T1 here, its length is A. No, length is not required. So it is T1 divided by its polar moment of inertia, it is T1 upon J1 into its radius R1. So R1 is equal to basically 2 times of half of this. So it is, suppose if it is, so it will be D1 upon 2. With this I can calculate the, and for this the torque is T2. So it will, maximum shear stress for this CB portion will be equal to torque of this upon its polar moment of inertia and into this. So its R will be D2 by 2. So with this I can calculate the maximum shear stresses of the corresponding two portions depending upon its respective torque. So this is the formula. So if I can put the value of T1 and T2 here, so that will give the value in terms of T. the angle of rotation at theta this C. If I want to know the angle of rotation at C, so that theta C will be same. So theta C will be same for both the parts. So if I calculate my theta C at this, either from this way or from this way, that will be same. That will be equal and opposites. If it is plus, then it will be minus. Since the nature of the torque are equal and opposite, so that the total torque theta B is equal to 0, it means theta of AB and theta of AC plus theta of CB is equal to 0. It means theta of AC is equal to minus theta of CB. So if I calculate my theta C either from this end or from this end, they are equal but have a different nature. If my torque here is like this way, then for CB portion it will be like this way. If it is like just like tensile, it is compressive. So it will be equal and opposites. So if I calculate my theta C from T1 side, it will be T1 into its length L upon N into its polar moment of inertia. Otherwise, from second portion, T2 into B upon J2. So either way, I calculate my theta. So this free body diagram will be like this. This is T1, and for CB portion, it will be like this. So T2. So their nature is opposite. It is just like tensile, it is just like compressive. If I calculate my theta C from this side, it will be T1, its torque is T1 into its length A upon N into polar moment of inertia of this portion. If I calculate theta C from this side, it will be T2 into B, its length upon N into its polar of moment is J2. So they are both equal and opposites. Show that theta B is equal to 0 means having the same nature. It is just like tensile, it is compressive. So it will be same. And suppose if A and B is equal to L by 2 and J1 is equal to J2 is equal to G, means it is just like this. This is junction where this T is applied. So it will be right from this right hand rule, it is clockwise. So it will be like this. So this will be like this, and I can say this. This is T2, this is T1. So in this case, if I put A and B is equal to L by 2 here in these equations, so it will be T into A is equal to L by 2, B is equal to L by 2 divided by N. So A into, and this is J2 and J1, both have the same dia. So dia is constant, so J1 is equal to J2. It means A plus B into J, and that is equal to T L square by 4 divided by N into, this is also equal to L. So this will be TL upon 4 Nj. So that will be theta C in this case. So let's come on the theory part. The reaction of a torsionally loaded The reactions of a torsionally loaded member which is restrained at both the ends are dependent not only upon the condition of equilibrium but also on the relative stiffness of the various shaft segments. So, as this was the case, its analysis not depend only on the statistical equilibrium. So, T is equal to T1 plus T2. This equation will not solve our purpose. So, we require another equation, that is the condition of compatibility. So, that condition of compatibility is this theta is same for both. Total theta b is equal to 0. So, its angle of twist for this portion is equal to angle of twist of this. So, this is another condition of compatibility. Angle of twist means that denotes its relative stiffness. So, it means static equilibrium, the reaction of a torsionally loaded member which is restrained at both the ends are dependent not only on the condition of equilibrium but also on the relative stiffness. Relative stiffness means angle of twist theta of the various shaft segments. So, both the equations of combined displacement, that is theta A plus theta B, and pertinent equation of statics are required to solve such problems. That's what I have explained. The former is based on this relative stiffness of combined displacement that based on the non-separability of the elements of the system and represented the geometrical dependence between the elements of the system. Non-separation means it's just like a monolithic as a unit. So, angle of twist, since both are fixed and this end is non-separable. So, this is a monolithic, this is no, you cannot separate it. So, angle of twist is basically same here. So, my total angle here would be the algebraic sum here. So, it is non-separable, it is a combined. So, this combined displacement is basically based on the non-separability of the elements of the system and represented the geometric dependence between the elements of the system. The deformation will be 0 in case the redundant constraints are fully rigid. Just like this case, both the ends are forced, so my total deformation angle of twist will be 0. And if elastic, suppose if elastic, then displacement are determined by the hook lags. So, if it is not, suppose if it is not fixed, then it will be the algebraic sum here, this plus this, theta of this plus this, theta of this. It will be determined by hook lags. If all the elements of a statically indeterminate systems are subjected to torsions, then the elastic displacement are expressed by angles of a twist. If all the elements of statically indeterminate systems are subjected to torsions, then the elastic displacement are expressed by angle of twist. So, theta this plus theta of this is equal to theta of this. The derivation I have explained. Let's another case. Composite shaft, compound shaft. Compound shaft means I have two shafts. Its length is suppose half of this. Two shafts are said to be joined in series and parallel. So, compound shaft means I have two shafts. So, whether they are in series or in parallel. So, two shafts are said to be joined in series if the driving torque is applied at one end and the resistant torque or the reactive torque at the other end. For shaft in series, both the shaft carries the same torque and the total angle of twist at the resisting end is equal to the sum of the separate angle of twist. Suppose there is no torque in between here and only my applied torque is at this end, which is free here. So, obviously my reacting torque will be equal to this one and my angle of twist here, theta b, will be sum of this theta AC plus theta of CB. So, here the torque is constant. Here the torque is constant and my Angle of twist is basically this plus this. So this will be the summations. So this series we can call as shaft are in series. So two shafts are said to be joined in series if the driving torque is applied at this end and the resisting torques are this reacting torque at this end. For shaft in series, both the shaft carries the same torque. So my torque will be same. For this will be T and for this portion also it will be T. So here torque is same. Only thing is that my angle of twist is different. And the sum of this angle of twist is plus this angle of twist will be the total twist here. It means my total angle of twist here will be this plus this. And torque is constant here. So this is the case of shaft in series. Another is here my theta here will be theta 1 plus theta 2. So this will be corresponding theta 1 is equal to TL1 upon N1 J1 plus this one. So this is the case of suppose if both have the same material, then N1 is equal to N. So T and N we can take common. So it will be L1 upon J1 plus L2 upon J2. Now second case is that two shafts are said to be connected in parallel if the applied torque is applied at the junction of the two shafts and the reactor torque T1 and T2 at the remote end. In this case, the angle of twist for both the shafts is same. This is exactly what I have explained in my derivations. So that was the case of parallel shaft or parallel, which I have explained here. So in this case, theta 1 is equal to theta 2 means so this is the case which I explained here in my derivations. This is basically a case of shaft in parallel. In this case, both ends are fixed and I have applied a torque here. So my this torque will be resisted by this end and this end. So here torque is varying for both the region, but angle of twist is constant. It is same for AC and for CB portion. So in case of parallel, this what I have explained here, the angle of twist will be same, but torque will be different. But in case of series, torque will be constant and angle of twist will be different. So this is exactly a case of shaft in parallel. So this is the case of shaft in parallel. As I have explained, theta 1 is equal to theta 2. Angle of twist is same for both the shaft, means T1 L1 upon N1 J1 is equal to this one. So T1 upon T2 is equal to L2 upon L1 this. If both have the same modulus of rigidity, same material, then this will cancel each other. So it will be L2 upon L1 into J1 upon J2. So this is equation number 2. Another is equation of equilibrium, that is T1 plus T2 is equal to T. This is what I have explained in my derivation. So both are equation. This is a condition of compatibility and this is a condition of equilibrium. From these two conditions, I can find my T1 and T2. So this is a case of parallel, and in shaft in series means my torque is constant but my theta is varying. So I have applied torque only at this end. So this is a case of shaft in series. So theta angle of twist will be basically the summation of this plus this. So here my theta is varying but my torque is constant. This is a case of series. Compound shaft. Compound shaft, what does it mean? Compound shaft means I have a two shaft. This is my core, and inside this core, suppose it is of brass. This is brass, and this is steel. So both have the different materials, and both are bonded, securely bonded, rigidly bonded. So they are behaving as a unit, as a single monolithic unit. So this is a case of a compound shaft. So this is my hollow tube. Inside is a different material. Suppose this is denoted by this T1 and this is denoted by 2. So This is a case of compound shaft. So here this total torque, suppose I have a torque T, so that will be resisted by this brass plus this steel. Suppose it is 1, this plus. So T is equal to T1 plus T2. This is my condition of equilibrium. Secondly, since they are rigidly bonded, so they have been securely they have been bonded, so they will behave as a single units. It means my angle of twist will be same for both. So whatever will be the twist of this brass, that will be the same, because both are behaving as a single unit. So angle of twist is same here. Theta 1 is equal to theta 2. What does it means? This T1, since L length is same, upon N1 J1 is equal to T2 L upon N2 J2. So L is, this is my shaft. So here like this. So length is same and it will be equal to T1 is equal to N1 upon N2 into J1 upon J2. So this is T1, and other equation is T is equal to T1 plus T2. So we can solve both the equations. So after solving, so this is a composite shaft made of concentric circular torsional bars that are firmly bonded together to act as a single member. This is statically indeterminate, as both have the different properties. So I have needed two equations, that is condition of equilibrium, another is condition of compatibility, means theta is same for this. Since both are rigidly bonded together, they must rotate by the same amount, that is angle of twist must be the same. So from this condition of compatibility, this is theta 1 is equal to theta 2 is equal to theta. So this is same. So T1 upon T2 is equal to this one. So from 1 and 2, if I solve this, so T1 will be this one and T2 will be this one. So after putting T1 and T2 value here, I can find my theta. So theta will be this TL upon N1 J1 plus 2G2. If I want to know the maximum shear stress F1, S1 and S2 for the core and the shaft, then it will be equal to this one. This is my core and this is my outside material. So T, it will be T is equal to T1 plus T2. So the corresponding maximum shear stresses, it will be different, and that will be dependent upon the T1 and T2. So T1 upon L is equal to F S1 upon its T1 upon J. T1 upon J1 is equal to Fs upon R1. So Fs11 is equal to T1 into J upon R1. So with this, no, it will be so Fs1, this Fs1 is equal to T1 into R1 upon G1, and this R1 is equal to half of the dia upon J1, and Fs2 is equal to this one. So if I want to know the ratio of Fs1 Fs1 plus divided by Fs2, it will be T1 upon T2, D1 upon D2, this will be, and J2 upon J1, and T1 upon T2 is equal to N1 J1 upon N2 J2. So if I put here the value, T1 is equal to N1 J1 upon N2 J2, T1 upon T2 here is in place of this D1 upon D2 into J2 upon J1. So this will cancel each other. So it will be N1 D1 upon N2 D2. So this will be the ratio of F1 upon S2. So let's illustrate the things by solving the numericals. So there is a question: a solid steel shaft ABCD as shown in the figure. This is a solid shaft. So it is fixed at both the ends A and B, and so this is solid shaft ABCD as shown in the figure, turns freely in a bearing at D. It is not fixed at D, it is turns freely and is loaded at B and C by torque. T1 is equal to this one and T2 is equal to this. So this is my shaft ABCD. Shaft ABCD. So this end is free basically. So it means this end is fixed and this is restrained. So this is fixed. And there are two torques. One is T2, 1500 Newton meter. It is T1 is equal to 2500 Newton meter. So both are anti-clockwise here. So this end is free, and the distance from this end to this is equal to 0.6 meter. This is 0.9 meter. This is 0.6 meter. So scale wise it looks different, but it will solve our purpose. The solid shaft ABCD as shown in figure turns freely in a bearing at D and is loaded at B. The shaft is connected in the gearbox at A that are temporarily locked in position. So this is my gearbox. It is means it is fixed. So it is locked here. Determine the maximum shear stress in each part. Number 1. So maximum shear stress in each part. This part AB, this part BC and CD. So maximum shear stress here FS1, FS2, FS3, that will be determined, and the angle of twist at D. Angle of twist at D means, since this end is free, so my angle of twist at this D end will be equal to the algebraic sum of the angle of twist of these three portions. So it will be theta D will be equal to theta 1 plus theta 2 plus theta 3. That will be the total angle of twist at D points. This is also required to be calculated. So dia of shaft is 80 mm and the value of N is 0.8 into 10 raised to the power 5 Newton per mm square. So this is the data given. So let's solve it. First of all, you represent your torque in this way. So this end is free, it means no torque is acting. At this C, it is anti-clockwise. So anti-clockwise means this is my right hand. You put your shaft here and put the anti-clockwise. Anti-clockwise means this way. This is clockwise, this is anti-clockwise. So this is anti-clockwise. So anti-clockwise here means this way. So my direction of thumb will this. So this way I can represent it. Here also it is anti-clockwise. So the direction will be the same. So this way I can plot it here. 1500 Newton meter and 2500 Newton meter. And this will be, since both have the same and this end only will have to resist the whole torque. So this plus this will be equal to 400 Newton meter. So that total 400 Newton meter torque will be resisted by this end, and that will be, suppose it is anti-clockwise, so it will be clockwise. So it will be clockwise, and clockwise means this way, is this way. So my thumb is in this directions. So I can plot its free body diagram. So if I want to draw the free body diagram of this portion, it will be like this. So it will be, suppose I consider this positive and this is negative. So it means for AB portion it will be like this. This is for AB portion. So this is 4000 Newton meter. So it will be 4000 Newton meter. And for this portion, so it will be equal to 4000 is acting in these directions. So this is 4000 which is acting here in these directions, and this 2500 is in these directions. So it means the net will be this. So this 1500 Newton meter will be this direction, because this is more. So 1500 will be here. So for this BC portion, it will be like this, 1500 Newton meter, and apply the exact equal and opposite. It's not required to be calculated here. And suppose if I want to draw for this portion, let us see here for CD portion it will be like this. This is CD portion. So my total force here is 4000 is acting in these directions, and this 2500 and plus this, they are acting, this plus this acting in 4000 Newton meter in these directions. So they are equal and opposite. So this is equal to this. It means net is 0 here, which is the case here. So in this case torque is 0. So if I know the maximum shear stress, I have to calculate for separate regions. So here the value of the torque is 4000. So F S1 will be equal to T1 L1 upon N into J1. So this value will be equal to T1 is equal to 4000 into its length. This is 0.6 upon N. N is 0.8 into 10 raised to the power 5 Newton per meter mm square, into its polar moment of inertia will be pi into d cube. So d is here, I think it is 80 mm. So it will be 84 upon 32. So this is my J. So this is N into J, and this is in Newton mm. So this 4000 is Newton meter. So if I multiplied it by 10 raised to the power 3, it will be Newton mm. And this 0.6 is also in meter. So again I will multiply it by this. So with this I can calculate my FS1. Similarly for FS2, for this portion, so torque here is, for this portion is 1500. 1500 it is Newton meter, so it will be Newton mm into L. L for this portion is 0.9. 0.9 meter into 1000, it will be in mm. So this is T1 L1 upon J N. Modulus of rigidity is this one, and its polar moment of inertia of this shaft will be, its dia is constant, or so it will be pi into 84 h to the power 4 upon 32. With this I can calculate my maximum shear stress for this portion, and for this third portion Fs3 will be, since torque here is 0, so if I put torque T is equal to 0, obviously it will be 0. So in this portion maximum shear stress is equal to 0. So this is the case. You can draw the free body diagram of this portion, and maximum shear stress for AB portion it will be this one. So it will come here 39.79 after putting in the formula. Oh, T upon J is equal to F upon R is equal to upon L. Oh, yes. F is equal to T upon J into R. So N is not required here. So I am sorry for that. So N is not required mistakenly. So with this formula, T upon J is equal to F upon R is equal to N theta upon L. So for finding this, F is equal to T upon J into this R. So this will be the formula for shear stress. So I can put T of AB upon J of AB into R of AB with this 39.79, and for BC portion it will be T of BC plus J of BC into this one. So this, and for the third portion it will be 0, since torque is 0 here. Second thing is the angle of twist. So angle of twist at D portion, means here it will be the theta of theta 1 plus theta 2 plus theta 3, sum of all these things. So it will be, so this is the free body diagram here. So theta of AB portion will be equal to, as the formula is, T upon J is equal to N theta upon L is equal to F upon R. So theta will be equal to, this theta will be equal to TL upon NJ. So this will be my formula. So theta of AB is equal to T of AB, L of AB upon N is constant, and J is also constant. So it will be, yes, so this is same. So T of AB is 4000 Newton meter. So if I convert in mm, it will be this one, into length in mm it will be 0.6 into 1000, it will be in mm, upon N. N is modulus of rigidity is equal to this into this one, into J. J will be pi into its dia raised to the power 32. With this I will get theta 1, theta AB. So theta AB will be this one, and for theta BC will be T of BC plus L of BC plus upon NJ. So that will be equal to, its torque here is 1500. So it will be in mm into length. Length is 0.9. So 0.9 into 1000 divided by NJ. So this will be this one, and theta of this CD portion is equal to 0. Why 0? Because if I put torque is 0 here. So torque is 0 means theta of this is equal to 0. So final total angle of twist will be this plus this plus this. and since it is just like tensile, it is just like compressive, so nature of the angle of twist will be different. Suppose if I consider this positive, so this will be negative, so this will be no, this will not be, no, both have the same nature. I think this is 4000 and this will be, yes, both have the same, so it will be plus plus, so this will be plus and this will also be plus. So final theta d will be this plus this. So it will be this plus this, which will be equal to, so this 10 raised to the power 4 6 into this 100 upon this pi into 80 32 into this n, this all I can take common. So inside it will be 4 plus 4 into this 6 plus this 1.5 into 9. So this will be the inside, and finally it will be 0.01165 radian. If I convert it in degree, it will be this one. Since pi radian is equal to 180 degree, so 1 radian is equal to 180 upon pi degree. If I multiplied it by 180 upon pi, so it will be in degree. So this is the value. Another numerical, a 50 mm diameter steel bar. This is my steel bar. Its dia is 50 mm. This one end is fixed and another is free, and there is a bore of 30 mm for a length of 250 mm from this end. So this portion is 250 mm, this is 350 mm. Total is 600 mm, and there is a torque of 680 Newton meter has been applied at this end. So a 50 mm diameter steel bar, 60 centimeter length and a 30 mm hole bored actually through it for a distance of 225 centimeter from this end. The dia is 650, and from this end for a length of 250 mm there is a bore of 30 mm. So your total length is 600 mm, and there is a torque of 680 Newton meter. So this torque has been applied at this end, 680 Newton meter. So find the total angle of twist in degree number 1. So my total angle of twist here, this will be obviously, so this is a case of series. My this end, this is my driving end, this is driven end. So torque is constant for this. My T is constant here for this and this. So there is no torque in between. So my total angle of twist as theta B, that will be, since this is a case of series here, so theta, this will be equal to theta of AC plus theta of CB. Since my torque has been applied only here, so this theta plus theta of AC plus theta of CB will be to theta at B. So theta B I have to calculate. Since my torque is constant, so this angle plus this angle will be the cumulative angle of twist here. This I want to know. Secondly, find the maximum value of shear stresses in the hollow and solid bar respectively. So for this portion, what is my F of CB and shear stress of this AC portion? This also I want to know. And the value of this N is equal to 0.75 into 10 raised to the power 5 Newton per mm square. This is given. So let's start. First I have to calculate this theta B here. So this will be obviously equal to, since torque is constant here, so my total angle of twist will be this plus this. So this is a case of shaft in parallel. So here torque is constant, same, and theta will be varying. So theta 1 plus theta 2 is equal to this theta. So this theta b will be equal to this plus this. And what is this? Theta of this portion, since torque is 680 Newton, so that will be in mm, into theta is equal to TL upon Nj. This is my formula. So this T into this length is 350 upon N 0.75 into 10 raised to the power 5 Newton per mm square into J. Polar moment of inertia of this one will be pi into d raised to the power 4 upon 32. So this is for this portion. This is for theta AC. And for theta CB, similarly, so torque will be same, 680 into 10 raised to the power 3 in mm. Length is 250 upon N is this one, and its polar moment of inertia will be pi into outside dia raised to the power 4 minus inside dia raised to the power 4 upon 32. With this, I can calculate theta of this and theta of this one. And when I add both together, theta this plus theta of this, will I get theta of B. So this will be my, so I can take my torque and N is constant, so I can take outside. So inside I will get this one. Since my this value torque and N is constant is common, so I can take common this. So inside it will be this one, and after it will be 250 upon this pi also I can take common. So it will be, so at 10, if I take 10 common, so it will be 25 upon 50 raised to the power 4 minus 30 raised to the power 4 upon 35 upon 50. So it will be this one. When I convert it into radius by multiplied 180 upon pi, so that will be in degree. So this is the answer. Secondly, Fs of AC portion and Fs of CB portion is also I want to know. That will be equal to the, so this Fs of AC portion is equal to, formula is T upon J is equal to F upon R. So F is equal to T upon J into R. So F of AC is equal to T of AC. This is obviously same. This is T into its radius. Radius will be 50 by 2 upon its J. So J is this one. So this way I can calculate this, and Fs of CB portion will be torque, this is common, into its radius. So its radius will be outside, half of the outside, and it's J. So J here will be pi into 50 raised to the power 4 minus 30 raised to the power, this is inside divided by 32. With this I can calculate Fs1 and Fs2, and this will be equal to 31.83 for CB portion, and for AC portion it is this one. So torque here is same for both. These are my value of shear stresses. So another numerical. A round steel bar rod ACB 1.8 meter long is firmly held at its end A and B. So this is my round steel bar AB. It has two parts, one is AC and another is CB. So its dia is 50 mm, its dia is 40 mm. The length of this part is 1200 mm and it is 600 mm. And there is a torque of 580 Newton meter here. So a round steel bar ACP 1.8 meter long is firmly held at its end A and B. So this is 1.8 meter. Both are firmly held, means fixed here. This and this. And total length is 1.8 means 1800 mm. AC is 1.2 meter B and 50 mm dia. BC is 0.6 meter and 40 mm dia. So this is 1.2 meter, its dia is 50 mm. This is 600 mm, its dia is 40 mm. A twisting couple of moment 580 Newton meter is applied at a junction here. Find the moment of resisting couples at TA and TB. So this is TA. Because of this, there will be a resisting couple, resisting torque here at this. Suppose this is TA and this is TB. So this also TA and TB needs to be calculated, and maximum shear stress in AC and BC of the road. So maximum shear stress in this portion and this portion means Fs of this AC portion and Fs of CB portion. One is this. Secondly, this TA and TB. So this is a case of shaft in parallel, we can say. So here there are two things, as I have explained earlier. Both the ends are fixed. It means my total angle of twist at this end, theta A or this, is equal to 0. So my theta B is equal to 0, since both the ends are rigidly restrained, they are fixed here. So they are firmly held in position. It means my angle of twist here is 0. So it means theta of this portion plus theta of this portion is equal to 0. So this is one condition. Otherwise I can say theta of AC portion is equal to theta of CB portion. So my theta of AC plus theta of CB is equal to 0, and that can be only when theta of AC is equal to minus theta of CB, means they are equal and opposite. So this is one condition, that is a condition of compatibility. Another condition is the condition of static equilibrium. That means this torque will be resisted by this plus this. So TA plus TB is equal to total torque. This is a condition of equilibrium. So this is a condition of compatibility. This is condition of static equilibrium. So with both the condition we can solve this question. So let's start. First of all, resisting couple at ends A and B. So let's plot this. Let's plot this torque in like this way. So this is clockwise. Clockwise means if I put my right hand, put this shaft by right hand, and this is my clockwise. Clockwise is this. This is my right hand. So this is the thumb. So it will be represented by double handle like this. This is anti-clockwise. So anti-clockwise means this way. No, so this is anti-clockwise. Put your shaft here and my finger will indicate the anti-clockwise directions. So this will be, my thumb is in these directions. So this is this way. and this is my TB. I can assume any of the directions here. So if value comes out negative, it will be opposite, otherwise the same. So suppose it is anti-clockwise here. It is clockwise, sorry. So clockwise means like this one. So these are my assumed directions. If I can draw the free body diagram of this ESE portion, it will be, so this is like this. This is TA. So obviously you apply here the same. This will also be equal to TA. And for this portion, it will be equal to, this will be equal to, otherwise I can say TB, or you can measure here. So this is TA and TB, this is T. This is T. Suppose if I say this T is more than TA, it means T minus TA. Suppose it is 30 and is 10, so it will be 30 minus 20 will act this way. So this will be obviously T minus TA, and same you can apply here, T minus TA. So obviously the value of TB is equal to T minus TA. So if I find the angle of twist of this one, it will be TA into formula is n theta upon L is equal to T upon GA. So theta will be TL upon NGA. So it means TA into its length, which is this one, upon N and J. So J is suppose pi raised to the power D raised to the power 4 upon 32. So this is my theta of this one. And here for this portion it will be, so T is equal to, this is my TA into length is 600 upon N into J, pi into raised to 40 raised to the power 4 upon 32. So my this plus this should be equal to 0. Otherwise you can say this is just like tensile, this is just like compressive. So this minus this, it will be minus. So both are equal. In this case, since my theta b is equal to 0, it means theta of AC portion is equal to theta of CB portion. So this is equal to this one. So n will cancel each other, pi upon 32, this will also cancel each other. So this 600, this will be 2. So 2 of TA divided by 50 raised to the power 4 is equal to T minus TA into its length is, so this I have cancelled, so it will be 40 raised to the power 4. So 2 times of TA is equal to T minus TA into 50 upon 40 raised to the power 4. So it will be TA will be equal to 2 plus 50 upon 40 raised to the power 4 will be equal to T into 50 upon 40 raised to the power 4. So I can calculate here TA in terms of T, and putting the value of T is equal to this, I can calculate my torque of this portion. So this will be, suppose this is my TA and TB. In this way also you can calculate. So TA is equal to this one, and my statical equilibrium is TA plus TB is equal to this one. This way also you can solve it, otherwise this way. So after putting this value, this TA will be equal to this TA will be equal to T. T is 580 Newton meter, Newton mm, into 50 upon 40 means 5 by 4 raised to the power 4 divided by, this is 2 plus 5 by 4 raised to the power 4. So with this you can calculate your torque of this portion, and it will be equal to this one. So TA is equal to this one, and TB is equal to T minus TA. So T minus TA means T is 580 minus TA, that will be this here. So this is the torque of this one and this one. So this is the respective torque of the two portions. So this is the moment of resisting couple at A and B that I have calculated. Now maximum shear stress in both the portions. Maximum shear stress means so TA is equal to 18.856. So it is 318.856, and T2 is equal to 261.14. So these are the value of this. So corresponding F S of this AB portion will be equal to F upon R is equal to T upon J. So F is equal to T upon J into R. So T here is 318.856 in Newton meter in mm, multiplied by 10 raised to the power 3, we will get in mm, Newton mm, upon J. J of this is equal to this much into R. R is the radius. Radius of this will be 25. So with this I will get Fs of AB. So Fs of CB portion will be T. T of this is equal to 261.14. This is in mm, upon its molar moment of inertia is be equal to this much into its radius, that will be 20. So with this you can calculate the respective shear stresses, and this will be equal to this much and this much. Let's comes to the another numericals. A horizontal shaft securely fixed at each end has a free length of 8 meter. So a horizontal shaft which is securely fixed at each end has a free length of 8 meter. So this is the case. This is a shaft which is fixed at both ends, and it has a length of 8 meter. So 8 meter is the total length, and they are fixed at A and B. Viewed from one end of the shaft, axial couples of 40 kilonewton meter clockwise and 50 kilonewton meter counterclockwise act on the shaft at a distance of 3.2 and 5.5 meter from the viewed end. So from this end, if I see from this end, it is 3.2 from this A. There is a twisting moment of 40 kilonewton meter is acting clockwise, and from this end at a distance of 5.5 meter there is another torque of 50 kilonewton, and this is anti-clockwise. So both are acting here. This is at a distance of 3.2, this is 5.5. So determine the end fixing couples in magnitude and directions. Means this TA and TB, resisting torque at B and A, they TA is equal to and TB is equal to, they are to be calculated, and find the diameter of the solid shaft for a maximum shear stress of 65 Newton per mm square. So dia of the solid shaft, suppose this dia is not given, so he has given the maximum shear stress Fs maximum is equal to 65 Newton per mm square. So dia of the shaft is also to be calculated, and position where the shaft suffers no angular twist. Another thing is that where our angular twist is 0, that is also to be measured. So this is the case. Let's start one by one. So if let's simplify this. So suppose this is acting in these directions, TB, it means it is anti-clockwise. So anti-clockwise means my arrow of the thumb is in these directions. This is anti-clockwise, so it will again be, this is anti-clockwise. Okay, anti-clockwise means in the direction, and this is clockwise. So clockwise means my thumb is in the direction. This is A. I can see anti-clockwise. Anti-clockwise means like this. So these are the direction which I have assumed. So TA and TB, suppose TA and TB are acting like this way. So let's draw the free body diagram. For AB portion, this will be like this. So this is TA, torque at A, and it is acting in this way. So this same will be here in opposite. If it is like this, it will be like this, and it will be TA. Now at this end, it will be equal to this TA upon minus 40. Suppose the value of TA is more. Suppose it is 50. It is 40 here. So it means it is 10 extra. Suppose this TA is 50. This is 40. So it means TA minus 40, that is acting in these directions. So suppose I assume this TA value is more than this. It means this value will be TA minus 40, and that will be extra in this way. So TA minus 40, same you will apply here, TA minus 40. So for this DB portion, my total torques acting in the directions, so this is acting this way. So TA is, and this plus this 50, both have the same direction. So it means the torque acting in this direction is equal to Ta and this one 50. Both have the same direction, and this direction is opposite to this one. This is 40. Suppose if I say this value is more than this value, so if it is 100 and it is 60, it means it is 40 more than this. If I assume this value is more than this, it means Ta plus 50 minus this 40 is equal to the net torque in the direction. It will be Ta plus 10. So this will be equal to Ta plus 10. Otherwise, I can say this Tb is acting here. So Tb is acting here. So this already I have used the status of condition of equilibrium. So here you can apply it later on. So this is my free body diagram. So here, as we know, so this is the free body diagram. So since both the ends are fixed here, A, so theta A is equal to theta B is equal to 0. So theta B is equal to 0. If I suppose calculate my theta B from this side, it will be Ta, this torque, into this length, this is 3.2, divided upon N into J. Since dia is constant here, so let's say it will be Nj. So, and here it will be Ta minus 40 into its length is 2.3 upon Nj. Since both have the same direction of torque, this is also just like compressive tires, so nature is same. Here, as I have applied this Tb here and this Tb, so its nature is opposite of this. So the angle of twist because of this will be opposite of this. This is just like tensile, this is just like compressive. So we will say it will be negative. It will be equal to Tb into its length upon Nj. So that will give the total theta B here, which is equal to 0 since this end is fixed. So if I suppose if I this plus this is equal to 0, it means Nj, this will cancel each other. So it will be 3.2 Ta plus 2.3 into Ta minus 40 minus is equal to minus 2.5 Tb is equal to 0. So with this I will get my equation in form of Ta and Tb. So Ta will be 5.5 Ta and minus 2.5 Tb, that will be equal to 40 into this 92. So this is my equation of compatibility. And another equation, as we know, this Ta upon Tb is equal to this one. So another is static equilibrium conditions. That is like this. So as we know, my total force acting in this direction are this one. This is Ta. T is acting in this direction. So let us start total torque acting in this way. This is Ta plus this, both have the same nature, plus 50 and plus Tb. So these are the torque acting in this direction. So this should be equal to the torque acting in this direction. So this is the only one which is acting here. So this should be equal to this one. It means Ta plus Tb is equal to 40 minus 50 is equal to minus 10. So this is from the equation of static equilibrium. So this is my equation 1, this is equation 2. I can solve equation 1 and 2. So then I will get Ta and Tb. So Ta and Tb will be equal to this much. So Tb is equal to 8.3575 kilonewton meter and TB is minus. TB minus means whatever direction I assume, that is actual direction is opposite of that. That's why it is minus. Minus means, this minus means this is not the right directions. So right direction is opposite of this. So this means this will be equal to, my direction is not this. This is clockwise. This is opposite of this. It 88.375 kilonewton meter. So if it comes out minus, it means just the direction is opposite. So it is 8.375 kilonewton meter. So it is, here it is so this one is 8.375, and this is, since it is positive, it means my direction assumed is right. So this is 8.375 kilonewton meter. So these are my torque here. It is clockwise, it is anti-clockwise. So these are the values. Now I have to draw the torque diagram also. So torque diagram is viewed from one axial couples of this is to determine the and fixing couple in magnitude and direction that I have calculated. And next is find the diameter of the solid shaft for a maximum shear stress of this much. So dia of the shaft is also I have to know. So also find the position where the shaft suffers no angle twist, means theta is 0 here. So diameter of the shaft I have to calculate, that is for maximum shear stress. So maximum shear stress will be occurred by maximum twisting moment. So it means I have to draw the torque diagram. My torque diagram will be like this. So this is the final position. As we draw the SFD and BMD, similarly we can draw this. So these are my directions. So suppose my torque in this direction from left to right, I consider it is positive, and this one from right to left I consider it is negative. So this is my baseline. So this torque is acting from left to right, it means I have considered positive. It means this is positive. 8.375 is positive, and from here to here it is constant. When I come here, it will be, this direction is opposite of this. So this is 8.35, which is positive, minus this will be minus, since it will be minus 40. Minus 40 means it will be minus 31.625. So it will drop. So it will come here. So it is 31.625 kilonewton meter. And from here to here, no extra torque is there. So this will be constant. And again, here it is, this direction is also 50, and this is plus. So this minus 31.625 is minus, plus I add this 50, I will get this one. So it will be again 18.375 kilonewton meter. So this is positive. This will remain constant from here to here, and then again, since this direction is, so here it will meet this. So this is my torque diagram. So from this torque diagram, why I had drawn this torque diagram, what is the purpose of drawing this diagram, is just to know where the maximum torque is there. So my maximum torque is this one. 31.6 Newton. So I have to calculate the maximum shear stress on the basis of this maximum torque. So as we know, T upon J is equal to F upon R. So this F maximum shear stress is equal to T upon J into R. So there in this T value will be this one. So my Fm max is equal to 31.625. This is the maximum torque into T upon J. J will be the polar moment of inertia. This will be this one into R. R will be, oh no, dia is not given. So this is D and radius will be D by 2. And that maximum shear stress is equal to 65 Newton per mm square, which has been given in the question. This one. So from this equation, this is equal to 65D I can find. So this D will be equal to 135.3. We can say 136 mm. So the diameter of bar is 136 mm. Now the last thing which remains to be calculated is I have to find the position where the shaft suffers no angular twist. No angular twist means my angle of twist is the 0. What is that locations? What is that position? That I have to calculate. So for finding the position of the point where my angle of twist is 0, I have to draw the theta diagram, means twist diagram. So let's see how it will be drawn. For drawing the theta diagram, twist diagram, I have to find the theta of the respective portion. So as both the ends are fixed, so theta of B and theta of A is equal to 0. So this is my theta diagram, twist diagram. First of all, you draw it. This is my baseline. So it is 0 here and 0 here also. My theta of this point, suppose if a theta C will be equal to theta of AC, and that will be equal to n theta upon L is equal to T upon J, means theta is equal to TL upon NJ. So theta C will be, T here is 8.375 kilonewton meter, 10 to the power of 6 in Newton mm, into length is 3.2 into 10 to the power of 3, this is in mm, upon N. N is equal to, so this is N, and is not given, this is J. J also you can say in form of NJ. So it will come out to 26.8 NGA, and this is positive. This I have considered positive. So it means this will be 26.8 NGA. So you can write in, this is 26.8 NGA. And what will the position of theta here? This will be the sum of this plus sum of this. So theta of D will be equal to theta of C plus theta of CD. This plus this. Theta C is equal to 26.8 NJ. And since here for this portion my torque is different. So it means theta of CD will be different. So since here the torque for this portion is 31.625 kilonewton meter. So this will be separate. So this is my plus and this is minus, so it will be minus. And value will be 31.625 into 10 to the power of 6. This is not Newton mm into its length. Its length is, this is 2.3 meter. This is total 5.5, so it will be 2.3 into 10 raised to the power 3 upon Nga. So this I will get, this will be minus 45.94, minus 45.94 Nga. So it will be 45, so minus will be here. So I will connect these 2 points, and as I know my theta here is 0, so connect these points also. So this will be my theta diagram. This is my twist diagram, and I have to know so this is the position where my angle of twist is changing its sign from positive to negative. It means at this point my theta is equal to 0. So this is the position where my angle of twist is 0, where there is no angular twist. So for finding this point, suppose this one is this triangle and another is this triangle. So these are my two triangles. One is this and another is this one. These are similar triangles. So suppose this position is x, so it will be 26 upon 8 Nj upon x is equal to this side 45.94 upon Nj into this will be 2.3 minus x. Nj and Nj will be cancel each other. So 26.8 into 2.3 minus x will be equal to 45.94 into x. So with this you can find the value of this x. The value of x will be equal to this much, 0.847 meter from C. This is from here, from this point, 0.847 meter. So if I calculate from this end, so I will add this 3.2 into this. So it will be equal to 3.2, this is 3.2 plus this. So it will be equal to 4.0473 meter. So this will be from A. So this is the position of the angular twist. So this is the position here. So this is my theta diagram, this is my torque diagram. So this is very good questions. So I hope you enjoyed my lectures. So that's it from my side for today's lecture. I hope you enjoyed my lecture. So thank you very much and good night.